Using an inverse matrix to solve a system of equations. A few videos ago, we talked about what an inverse matrix was, then we learned how to find an inverse matrix, and now in this video we'll learn how to apply the use of an inverse matrix to solve a system of equations. Let's first take a look at what you've learned before. Students learn that an equation like 4x equals 7 can be solved by either dividing both sides of the equation by 4 or multiplying by 1/4. Remember, when you multiply by 1/4, that's the same as the multiplicative inverse. This concept still applies with matrices. The difference is that the multiplication used is the inverse matrix. In the next paragraph, the letters A, X, and B all stand for matrices. So if we start off with an equation that says if matrix A is multiplied with matrix X and it equals matrix B, then to solve for X, the inverse matrix is multiplied on both sides of the equation. And that looks like this. Multiply the inverse matrix on both sides of the equation. Well, that becomes just X equals the inverse matrix times B. And it becomes that because we know A and A inverse are inverse matrices. So when they multiply together, the result is an identity matrix. Let's come down below where we can see that a little more in action. If I start with A times X equals B, and I multiply both sides of the equation by the inverse matrix of A, then the inverse matrix of A multiplied with A becomes the identity matrix. And we know the identity matrix, when multiplied with any matrix of the appropriate size, just gives us back that matrix that we multiplied by. On the right hand side we have A inverse, or the inverse matrix of A, that we're going to multiply with B, and with technology that is pretty manageable. So let's apply this to solving an actual system of equations. I'm going to use technology to arrive at my answers. Okay, first let's start with the example. It says solve a system of equation 3x minus 2y equals -6 and 4x plus 3y equals 10 with inverse matrices. So I'm going to begin by taking all the coefficients in front of x and y and the constants at the end and place those in particular matrices. The first matrix A has all the coefficients for x and then all the coefficients for y. And matrix B at the end has all the constants, the -6 and 10. You'll notice that matrix X here, capital X versus smaller x, has our variables x and y from our equations. So that's an important setup. You take all the coefficients, place them in A, place your variables in x, and then your equal sign and your constants. Once that is set up, we need to calculate the inverse matrix of A. I did that with technology. We took A and with technology found the inverse matrix. To go back and solve my equation, AX equals B, I'm going to solve that by multiplying both sides of the equation by the inverse matrix. Okay, so here's my work for that. I have the inverse matrix of A being multiplied with A, and the inverse matrix of A being multiplied with B. But the inverse matrix of A multiplied with A gives us the identity matrix. So I have the identity matrix, I have our variable matrix, and the right hand side with technology simplified down to this new matrix on the right hand side. When we take the identity matrix and multiply it with matrix X, we get matrix X, and now we've arrived at our answers. So we know the ordered pair that would have solved this system of equations is the ordered pair 2/17, 54/17. So that may seem like a lot of work, and we also learned how to solve a system of equations by graphing, the substitution method, the elimination method, and with the Gauss-Jordan method. So now you have another method for solving systems of equations.